Hello, everyone. I'm going to be going over section 27, and I'm going to be going over applying gradient descent. So this is going to assume that you've gone through all of this. I'm not going to be going over this actual lab. I've got an example myself that I made that I will be going over. So first things first, I want to look introduction to gradient descent. I want to look at this lab or this README. It has a pretty nice introduction to the kind of the steps that I'm going to be following. Yeah, so here it is. So step one, we're going to choose a regression line with a guess of the values for n and b. Calculate some sort of error function. Then you adjust the m and b, and then repeat this process. Calculate the RSS and adjust the n and b. And what we're going to do here is eventually get the n and the b to be the best that it can be. So first things first, I want to import pandas. It's PD. I think that's all I'm going to import to start. I have some images here that I will show in a little bit, so I have them suppressed. And I have this data set. I believe I got this from Kaggle. It's been a little bit. So I have this data set, and let's look at the columns. It's a data set about different houses, similar to the King County data set. I want to look at my X. This is the variable. I'm just going to be doing a single variable regression to start. I want to look at the living area, and I want to use that to predict sale price. So sale price. And let's plot this out. Import matplotlib.pyplot as plt plot.style.use ggplot plot.xkcd matplot lib.pyplot. And I want to now plot this. Plot.scatter. Living area, and plot.y label is sale price. So living area and sale price. So we see the kind of the trend is that as living area increases, the sale price increases. I do have these two houses right here that do not follow this trend, and I'm going to end up removing those because I'm all right with outliers, but that follow the trend. These points right here, when you're doing regression, it's going to try and pull the regression line down. And these points will, and I know that it looks like the trend is mainly this way. I don't want it pulled down in that direction. So that's a good way to kind of think of how to, whether you should remove it. Does it follow the overall trends? Like these are just huge houses, but they're also really expensive. These are huge houses, but they're not very expensive, which I don't really trust. So let's figure out what points these are. So I want ground living area greater than 4,000 and sale price. I want that to be less than, what is that, 300,000? 300,000. So I got these 2 points. So now I know their indexes, so I can remove them now. So I want to remove, what is that, 523, and I want to remove 1298. in place equals true. And since I'm dropping values, I like to reset the index. So nice. So now let's rerun this just to kind of verify what we did. It looks all good. And it doesn't, but that's because I made this X and my Y variable. I need to reset this. So now that looks good. So now I have a pretty good line there. And then just for fun, I want to look at what the correlation is. That's GR area sale price core. The correlation is 0.73. So should be able to get a decent result here. And what the process that I'm going to be doing, I'm going to be taking a derivative multiple times, and let me do it on whiteboard. And this is the x-axis, your y-axis is going to be error. And this is going to be, if we remember, we update the slope and the intercept multiple times. So this is going to be a number of times you've updated it, so number of times. And what you'll get is a plot that kind of looks like this. And it'll eventually level off, and that should be straight. It shouldn't go up. But right here, this is where the model is converged. And it will converge a lot faster if we normalize the data, or if we if we scale the data down. So that is what I'm going to do first. So I'm going to take each of my x's, ground living area. I'm going to subtract it from the mean. And then I want to divide it by the standard deviation. So this is doing a z-score transformation. And there's a library that'll do this too. The standard scaler, I believe, in scikit-learn. Sklearn, standard scaler. Yeah, so this is the same thing I'm doing. X minus the mean divided by the standard deviation. It's pretty easy function to code out too, so I'm completely fine with it. So first part of this is I'm first going to choose random values of m and b. And just for fun, I'm going to be doing my slope is equal to 0, and then my intercept is going to be 0. So we know that probably isn't going to be 0, 0, because we know there is a slope to this, and looks like there might be an intercept too. So, but we're choosing something random, so that is what we're going to do. First thing I'm going to do is make a function to make a regression formula. And intercept. And I'll talk through this as I write it. Slope. So this is going to calculate the y equals mx plus b plus my intercept. So what this is going to do is it takes in an x value, it multiplies it by the slope, mx plus b, and returns it for you. And then I'm going to write a make a graph, and I want to show my data, and I want to show my best fit line. So first step, make my plot 12 by 8. That's kind of my default plot style. And let's do this, and we'll steal all this. So this is my graph. The font size a little bigger. I can barely read it. So there's my graph. Now I want to plot my line. So I want to do a line plot for that. Plot. And my x is going to be x, and my y is going to be this regression formula. So this is why I did that. So x, and I want to put in, so first this x, then I want to put in my slope, which is this, my slope and my intercept. And let's make the, let's add a label to this. Label equals raw data. Label equals regression. And I want to make the color for this color equals black. And plot.legend. So here's my data, here's my line, definitely not my best fit line. So after testing it out once, so now I want to calculate my residual sum of squares. For this, I'm going to write another function. So I need to write some sort of function to calculate how good or how bad did I do. And I did pretty bad here. So let's see how far each point is from the line. So I'm going to, like I said, write a function. I'm going to call it error. I'm going to be using these functions later. So let's put in intercept, slope, and then what my x and my y is, because I need the actual label. So total error, start with 0, and I'll be adding to it. So for I in range 0 or length of x. And then my total error is, I'm going to add to it each time, is going to be y I minus, so this is going to be each of my target variables, and minus my my prediction. So that'd be slope times x of I plus intercept x of I plus the intercept. Intercept doesn't change, and then I want to square it. And then return, I want to return the total error, and I'm going to divide it by the length of x to normalize it, to get it on the same. So let's run this. My intercept, my slope, x and y. So I end up with a very large error. What is that? That is, let's just take a look at it. This way. So I'm, what is that? $39 billion off, which is a huge number. But that's kind of to be expected, right? This is a terrible line for this data. So I can finally show off what I'm hiding. So I have, this is my error function, y minus mx plus b squared, divided by the count. And what we're looking at here is, so kind of going back to this, my error right now is right here. I want to go down. So in a, in a three-dimensional space, or my error is probably like right around here, very, very bad. I want to get to the bottom of this. There's a theoretical bottom to this. And if you rotate this thing, we can see the actual, like it's here. This is obviously, we don't know what this plot looks like. So what we can do is take these partial derivatives and to get the slope at this point. And these are partial derivatives. First one is the partial derivative with respect to your slope, m, and then this is your partial derivative with respect to your y-intercept. And I will show how to use that, how we can use that to adjust our mn and our b. So I'm going to make another function called step gradient. So b current, m current, x and y, and learning rates. So I'm going to start with a b gradient, 0, m gradient equals 0, n equals a length of x. And I'm going to loop through all my x's again for I in range of length of x. And then, not what I wanted to do. I'm going to, for each of my x's, I'm going to plug them into this and add to this b gradient and m gradient. So let's start with m gradient. So I got a -2. I'm going to move this negative exponent, this negative part out. So -2 divided by n times so x of I times y of I minus m current times x of I plus b current. And do the same thing with the b gradient. I just realized I got some spelling errors. Gradient. So same thing, -2 divided by n. There's no x on this one, so it'll just be times y of I minus m current times x of I plus b current. So I got my updated m's and my updated b's. So let's go back up to my graph. So I put in this variable called learning rate. So if I plug this right in, if I start right here, I want to just inch down toward this theoretical minimum. If I don't put in a learning rate, it could go from all the way over here to all the way over on this side, where it just, like, imagine if you're right here, you could skip that local minimum, that minimum right here, and keep going up. So you will multiply your m gradient and your b gradient by a very small number. And another thing, I'm going to subtract it because I want to go down this down the slope. So new b is going to be my current b, and I want to subtract that from learning rate times my b gradient, and do the same thing with new m current minus learning rate times my m gradient. Return new b, new m. So let's run this. So I'm gonna call this first step, and this is gonna be step gradient, and this is gonna be my intercept is b. my slope is mx, y, and my learning rate is going to be, I'm going to set it to be 0.1. So this is my new slope, or my new intercept is mx. Yeah, my new intercept and my new slope. So let's plot this again. I'm going to steal my code here. And now I have, so my slope is going to be first step, and it's going to be 1. And then I have first step to a 0. This is my inner. First step 0. So let's take a look at, so I start out with a very flat line. I'm starting to inch up a little bit. So this is just my first time through. Now, kind of going through, calculate the RSS again. So error, this is going to be, and let's grab the original error as well. I want to look at that so it's easier to compare. So huge number, error, and I don't remember the function. I should have done, so intercept, then slope. So I'll do first step. I want intercept first, and that is the first thing, y equals mx plus b. So the first element, then my second element, then I want x and y. So already the error is decreasing a little bit. So cool. I want to make another graph that calculates all this, and I also want to print the error on this thing. Plot.text. So let's put it at 0, 600,000. And I want an F string. Maybe make it -2. And make the font size a little bit bigger. I can barely see that. Font size equals 18. So here's my error. So I'm going to eventually put this in a for loop. So that's why I want to do that. So, but first let's do, so I've done it once. So let's repeat the process, iteration number 2. Number 2. And so that takes B, then my M. So that is going to be first step, X and Y, and then learning rate is going to be 0.1. And then let's plot this out again. And instead, I want to put second step in here. So error is still decreasing, and the line's starting to get a little bit closer. Let's do a third iteration, then I'll put it in a for loop. And I'm going to copy this down, make it a little bit first. Third step. I want this to be second step. And second step. And this should be third step. And third step. You see, this is kind of a repetitive process. So this is really good candidate for a for loop. So getting smaller. So let's do it. Let's run it. Let's run it a. Why am I drawing a blank? Let's run it 100 times. And I want to time how long this takes to run because I'm kind of curious to see how many steps we should run. I want to print out my error. I want to save my errors because I want to make a plot kind of like this to see if 100 iterations I start seeing it level off or no. I want B is going to start with 0. My N is going to be 0. So for I in range of 100. So let's first calculate the error. B in X and Y. So append it to that list, and then we'll update my B and my M. And 1.1. So it took 11 seconds to run. And that converged pretty quick, actually. This is kind of exactly what we're looking for here. Is it reaches its theoretical kind of maximum here, right around this like 10 number. So let's maybe do run this again, but we'll run it 20 times. I'm just going to steal this code again. But each time, this time, I want to print out this this guy right here. I want to update it afterwards. So I'm changing that. Regression formula is X, then it is M, then B. Cool, then my error function is B, then M. Should have made this a little bit more consistent. B, error function is B, then M. Error function B, then M. Error is, why am I messing up? Error is M, is B, then M, is B, then M. It is B, then M. I'm getting mixed up on that. B, then M. And each time through, I want to plot.show. And I also want what iteration number we're on, plot.text. -2. We'll put it at 500,000. And I want to stop that right off the bat. I can't read that again. Font size 18, and I'm doing I+1 because it starts at 0. So iteration number 1. Number 2 starts improving. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And the error is still going down a little bit. But let's print out my errors again. Plot range at 20. I want errors. Cool. So yeah, it converged a lot faster than I was thinking it would. Something that might be kind of cool to do is let's plot out the error as well. So I want iteration number. Let's put a title for the iteration number. Plot.title. Iteration number. This one. Make sure that's right. And what am I doing wrong? I don't want an axes. Oh, I need to do axes 1.scatter. Okay, that looks good. I'm going to stop it. I'm just trying to make this kind of a little bit nicer. I just kind of had an idea that I thought of. I want to remove the, so I got the iteration number. Now I want to plot the, make my second axis. Make this an F string. And see what you can see is you can see the error as it goes. And I'm going to make this a little bit, make the number of iterations increase a little bit. Let's do 100 iterations. My computer is not liking what I'm doing. Plotting out a bunch of images like this can be kind of computationally intensive. The fan on the processor fired up. But like you can see, the error is definitely leveling out. We are on number 24. Is the error still going down 20 to 38? And the nice thing about this is that as you get closer and closer, it only is going to move the slope and the intercept a little bit. You usually will not jump it if you make a small learning rate. Yeah, it looks like we've converged for a while, but still good to see. Now we're at 91. We're at 100. Cool. So I'm going to import scikit-learn and see what the results that we got were. So I got an M and a B, ended up with that. These numbers, 1, 2, 3. All right. Can't remember. Scikit-learn. Import linear regression. So let's make an instance of it. And since I'm just putting in a single array, I'm going to have to do the reshape. Values, reshape. Values, reshape. So let's look at the coefficients that we got. Don't remember how to get the linear regression coefficients. I don't know, let's try and find it this way. No, intercept, of course. All right, so I'm gonna make, for the grand finale, gonna look at make two plots showing the best fit lines with the slope and the intercept. I also want to plot out the error. So I'm gonna just kind of walk through this line by line. So make it 12 by 8. My first graph, this is gonna be my gradient descent graph. 1. And I'm gonna steal some of this code because I think it'll be a little quicker. Oh my gosh, I forgot this is so freaking long. So I want to do axis 1 dot plot. All right, and I want XY, raw data, living area. And my regression formula is M and B. And then my last step is B and M, I believe. B. I do need to do plot. All right, 29038. I just want to double check 29038. Yep, that looks right. And I'm going to move this up to maybe 800,000 and then make this size 16. Dot label. I'm going to call this gradient descent. Oh, I want title. And let's add some more text. Plot.text. I'll do -2 700,000. Import numpy as np. So slope is 58,000. I don't know why I didn't just copy that. Put that in B. Intercept, what is that, 180,000? Yeah, I was looking at this earlier, thinking, why is it not crossing? But this is actually 0. So it's crossing the y-intercept right here where it's a 0. So that's my gradient descent. So I want to do the same thing, but with scikit-learn. And I want M is this thing. X plus B, so there. My B is this. B is that. M is that. So scikit-learn, V, M and G, B. Oh, and then I want to change this. So this is going to be my B. And then this is going to be my M. And hopefully this is all right. Oh, I need to specify what axis 2 is. So interesting. I get pretty close, or I get exactly the same, rounded to 2 digits. But do I get the same error? 29038 34185 3368. Yeah, I'm getting very, very close numbers. And that's a good thing. It shows that scikit-learn is pretty accurate. So hopefully that's all that I have. Hopefully that was useful. And if you have any questions, let me know. Thank you.